folks, this is Scott Weingart, and you're listening to the EMCrit podcast. Okay, so as promised, this is going to be the first part of what is probably going to be a 3 or 4 part series on acid-base in the ED. Now, this is really hard stuff, and it's going to call on you to dredge up some basic science from med school or wherever you did your preclinical training. And it's something that might be confusing first time around, but I think I could promise you that by the end of it, you're going to have an understanding of acid-base that you'd never had before. And as such, it'll kind of become intuitive instead of a kludgy, never really quite getting it, but using memorized rules and not understanding why. And I always hated that. I hate that on ventilator management. I hate that on acid-base. And just as one further preface, I never really did pre-medical science. As you'll hear in the course of the lecture, I had to teach myself, and I taught myself mostly from PChem books, physical chemistry books. And as a result, since PChem embraces a lot of the stuff that comes before it, like inorganic and organic chem, I don't really know where the dividing lines are between those subjects. So if I call something PChem and it actually turns out to be organic chem, don't fault my instructors. I didn't have any. You could just fault me. All right. What I recommend doing is listen to this first lecture, and then I have a PDF that I link to in the show notes. I recommend you print that out, you read that article, and that'll reinforce a lot of the stuff we're talking about. Part 1 is kind of an introduction to some of the concepts you'll need to understand this stuff, and then in Part 2 and in the further parts, we'll really apply it to our patients in the emergency department. So as always, write me if you have any questions or comments, and let's get started. So this is the acid-base talk. It's really why you suck at acid-base. A few years ago, there was a whole YouTube campaign on why you suck at Photoshop, and it's pretty hysterical. Nick, I know, is a big fan. If you want to check that out, you'll see where the inspiration for this particular didactic methodology came from. I'm still not taking money from anyone. I get no funding. It's all because of the bias that's injected whenever you're taking money. So I've avoided that. So what you're hearing is just my opinions. So this is a lecture about the fact that your medical education has failed you. All across the world, there's a whole bunch of different theories on acid-base management. And unfortunately, the places you got your training, which is medical schools in the United States, really get it wrong. They pretty much suck. And the reason they suck is this blind and really inexplicable devotion to Henderson and Hasselbalch. So why does Henderson-Hasselbalch methodology for acid-base suck? Well, there's at least 3 reasons that come to mind right off the bat. And the first one is the steps necessary to use it correctly are not prescribed. And even if you did know what they were, chances are you're not doing them. Second reason is, in its current form, it's inaccurate in real patients. It works just fine when you have some problems on your in-service, because they were predicated on using Henderson-Hasselbalch. But when you try them on real patients, they're grossly inaccurate. And I have some studies to show you that. And then, even if you did everything right, it doesn't really suggest appropriate treatment because you don't understand what the problem is in the first place. So you don't really know how to fix it. Now I'm being kind of unfair to Henderson and Hasselbalch, because after this lecture, what you'll find is that if you understand the approach I'm laying out, then Henderson-Hasselbalch works just fine. So really the problem is that Henderson-Hasselbalch hasn't been explained in a way that allows you to use it. So in order to get this, you have to understand first what determines acid-base. All right, so this is the answer to that question, and we really could stop the lecture there because this is everything you need to know. And now, just looking at that, you pretty much understand, and so there's really no point in belaboring any of this. All right, well, if you wanted some explanation, we could go a little further. So the first thing you have to understand is that I'm not a science guy. All right, I was a humanities and medicine major. That's how I got into medical school, through Sinai's humanities and medicine program, and I didn't take any pre-med sciences. And the fact that people wanted me to take pre-med sciences in order to become a doctor is why I wasn't planning on becoming a doctor. And then Sinai goes around and recruits all sorts of jokers with long hair like me who is doing philosophy or linguistics, and they say, we'll make you a doctor anyway. And I'm like, oh, okay, that sounds good. But I didn't do any organic chemistry, I didn't do biology, I didn't do any of that crap, and I certainly didn't do P-Chem. So I had to teach myself all this stuff later on in the course of residency. And the reason I had to do that is to understand acid-base, because if you don't have a good understanding of physical chemistry, then you can't really get this. And then you're just basically memorizing formulas, and that's where we run into all the problems. So the first thing you have to understand is conservation of charge, which means your body needs to be neutral. That's part of homeostasis, and you can't have the lack of neutrality. Your body will always generate neutrality no matter what in your plasma and the rest of your solution areas throughout the body. The next concept is the difference between independent and dependent variables. Okay? The independent ones are the ones that change. The dependent ones are changed by those independent variables. That concept you all get, but to understand what are the independent variables in acid-base, it's kind of mind-blowing. So the first thing to get is that the body is a limitless pool of H plus and bicarb. There's no end to it, and therefore they can't be independent variables, even though everything you might have learned up until this point makes you think that acid-base is determined by the amount of H plus you have in your body. It's not. I mean, that's what determines pH, because that's what pH measures, but that H plus is a dependent variable. You could generate as much or as little as you need based on other stuff. So then the question is, what is that other stuff? And this is that other stuff. This is the full range of the independent variables that determines acid-base. Now, stop me if you guys have any questions about any of this as we go on. This is an interactive lecture, okay? So the independent variables are carbon dioxide. Now that one you know, right? That always made sense. If the CO2 goes up, you're acidotic. If the CO2 is down, you're alkalotic. That's easy. Then there's this concept of total weak acids, all right? You've probably never heard about that. We're going to talk about it. And then the strong ion difference, another one you haven't really probably heard about unless you've heard my lectures or some of the other quantitative acid-base guys. So another way of saying those latter two is weak acids are essentially albumin. Albumin is the weak acid we care about in the body. Now, for me to tell you that albumin's actually an acid, right there, like most of you haven't heard that, right? How many folks knew albumin was an acid? Raise your hands. All right, not so many. Kit knows because he was here the first time I gave this lecture. So albumin actually has a big role in determining your acid-base status, and yet I think during your medical school, Henderson-Hasselbalch guys never mentioned that a single time, right? Okay. And then strong ions, you have some glimmer that they're related to acid-base, though they never really told you why. Does anyone know what a strong ion is? All right. So if you take salt, right, regular table salt, NaCl, what happens when you put it in solution? Yeah, so Seth says it dissociates, and all that means is it splits apart. There's no more salt, NaCl, linked together once it goes into solution. Any anions or cations that completely dissociate in solution are considered strong. And weak, therefore, means that they're not going to fully dissociate. And how much they do is dependent on the pH of the body, at least for human physiology. So albumin, some of it is going to have its H plus locked onto it, some of it is not, and that's going to be dependent on the pH of the body. That's why it's weak. Strong always dissociates. Not that important that you're getting all this yet. Just try to let the concepts percolate. All right, this is just a demonstration that those are indeed the independent variables, that all of them, when they vary, pH changes, and they do that independent of the other two. All right, you don't have to go any further into this. So we started talking a little bit about the strong ions. They completely dissociate. The two important ones to remember are what makes up table salt. Sodium and chloride are the prime determiners of metabolic acid-base status. Now that's kind of weird, right? Why the hell is sodium and chloride coming into acid-base? They have nothing to do with acid-base, but they actually are the prime determiners of acid-base. So strong cations are anything with a positive charge after they fully dissociate. The primary one, like I said, is sodium. And strong anions have a negative charge. The primary one you care about is chloride. The difference between the two, the strong ion difference, is the major determiner of acid-base. So what is the normal difference between your sodium and chloride? Nelson? Yeah, 40 is a good estimate. The number we use is 38, but 40 is just fine, and that's predicated on a 140 sodium and a 102 of your chloride. And that 38 is a good pH determiner. If that number shrinks, so let's say your sodium's 140 and your chloride's 120, so now instead of 38 you have a 20 difference, that makes the patient acidotic. Why? Well, if there's more negative charges than there is supposed to be, and we know that your body has to stay neutral, what does your body do to counter that extra negative charge? I hear H+. Who said that? Seth. Okay, so that's exactly what happens. That limitless sink of the ability to generate H+ or bicarb just puts out some more H+. Now let's say we did it the other way. Let's say your sodium's 140 and your chloride is 90, which is a 50 difference, which is greater than it's supposed to be. What happens? What does your body generate? It generates extra bicarb, right? Yeah, it generates extra bicarb because you have to match that extra positive charge with a negative charge. And that's why those are dependent variables. The independent variables are leading to the situation that causes the generation of either H+ or bicarb. And I could give you the derivations of all this. I could take you through the formulas of how this happens. I could give you evidence that it does happen. I'm going to leave that aside for now. I'm happy to talk with anyone who wants it. I don't think you guys want that. If you're willing to accept, and I think by the end of this you will, that sodium and chloride, or really for that matter any strong ions, determine acid-base and cause the generation of H+ or bicarb, then you will have had enough information to use this system. All right, so that's the strong ions, and we said the difference between them is a prime independent variable for acid-base. Then we talk about the weak acids, and it's just a physical chemistry fact that albumin actually is an acid. So if you accept that, and you have to, I could prove it to you, then you could accept the fact that the concentrations of albumin in the body are going to have effects on the patient's acid-base milieu. All right? And since we said it's a weak acid, that will vary depending on the patient's pH, but for all intents and purposes, it doesn't matter to you. The differences between that dissociation at pH of 7.4 and a pH of 6.9 is so minuscule that you don't even have to worry about it. So what we can say, for all intents and purposes, is that if your albumin goes up, then the patient will be more. What's that, bud? Well, we said albumin is an acid, and if albumin levels go up, you're acidotic. And if albumin levels go down, you're alkalotic. And then that next step you have to grasp is that this is not an absolute. We're not measuring the total albumin in the patient's body. What do we measure? Right? When you get an albumin level on a lab, what are you measuring? Well, but the serum albumin is, the unit it's given to you, is it grams? Is it milligrams? No, it's not. It's milligram or grams slash a volume, right? Do you guys get that? Do you get that? Pretty much everything you're getting labs on are a weight per volume, not an absolute weight. We don't get the patient's total body sodium. We get their milligram per deciliter sodium or millimoles per liter sodium. Same thing with albumin. Now, why is that important? It's important because if you have a patient who's profoundly dehydrated, their albumin might be quite high. But then you fix that patient, and what happens to their albumin? It drops, right? So this, in particular, is going to change over the course of the patient's illness and the course of the patient's treatment. And so these weak acids are varying based on what you're doing to the patient. Now, so are those strong ions, but we don't even have to think about those because we always take that into effect, right? But the albumin, on the other hand, we don't think about that. We get one albumin at the beginning of the patient's course and we pretend that's their albumin for the next 4 days. It's not. It's totally varying. I mean, we get the sodium once or twice a day, but the albumin we don't. So bear in mind that these are all concentrations, not absolutes. All right, so we said there's 3 independent variables that determine all of acid-base. And that's all we really have to worry about is your carbon dioxide, your strong ions, and particularly the difference between them, the cations and the anions, and the concentration of weak acids. The only one that really has any power is the albumin. The other ones are things like phosphate or sulfate, which rarely change to a level that matters to us clinically. All right. Last concept on these variables is the strong ion gap. The way to think about that is just substitute the word anion gap, and for all the purposes we're going to be talking about, it'll be a easy substitution. So what you were thinking about as anion gap, we're just clarifying and saying it's a strong ion gap, because that's what we really mean. Like, name some things that make up an anion gap. Well, no, not to calculate it. I get where you're going, Jake. Not to calculate an anion gap. Would actually fill the anion gap. Lactate. Very good. What else? Keto acids. Excellent. Any others? Sure, toxic alcohols. Very good. So those are the things that are going to also make up the strong ion gap. The reason we clarify the term is because it could really go both ways, right? You could have things that are strong cations, which we don't really talk about as much, that can make that gap actually negative, right? So anion gap's already a misnomer by that virtue. But the other thing is that let's keep it on the same page that we're talking about strong ions, because we want to be as quantitative and precise as possible. But if in your head, every time you see this SIG, you put in your mind anion gap, you'll be just fine. All right. How many folks know what a base deficit is or base excess? You see it on every single ABG, and most of you just ignore it. Who could give me a concise explanation of what this actually is? Dan? Well, that is a good use of the words, but let's not wrong. But let's see if we can zone in a little. Sure, you're getting right to it, but let me give you the strict definition because I think it'll be helpful to you. The reason this is on every single ABG. All right, so the reason base deficit or base excess is on your ABG is because it's a hugely important piece of information for you. Now, what this is they take the blood gas sample and they get rid of the respiratory component. They normalize that to a CO2 of 40. They just do the math. And they pretend, no matter what the CO2 is in the real sample, they change the numbers so that it was as if the CO2 is 40, thereby eliminating the respiratory component of the acid-base mix. And so now you're left with a representation of purely metabolic acidosis. This is huge. This means you don't have to worry about the respiratory side if you use the base excess or base deficit. Now, then what they give you is a number, and that number is how much base or acid you would have to add in order to get to a pH of 7.4. So let's put this in real terms. Let's say you get a base excess of -6. All right, a base excess of -6. What that is saying to you is that this patient has 6 millimoles per liter of base that would have to be added to the patient in order to get a pH of 7.4. All right? So a base excess of -6. What the minus means is they have a base excess in the negative, meaning they have a base deficit, right? You follow that, guys? All right, so base excess in the negative means they have a deficit of base, which means you'd have to add base to get them neutral. Let's say they told you you had base excess of 4. That's telling you they have 4 excess base, meaning you would have to add 4 millimoles per liter of acid in order to get them to a neutral pH. Now, almost every lab I've seen have put the terms in base excess. If you see the term as a base deficit, it's just the opposite. It means if they have a base deficit of 4, that means they need 4 of base, right? And if they have a base deficit of -4, it means they have an excess. And then the negatives kind of get confusing. I like the base excess. Base excess is easy. If it's positive, they're alkalotic, you need to add acid. If it's negative, they're acidotic, you need to add base. Does that make sense? What it means is you could look at any ABG or VBG, see the base excess and know immediately whether the patient has a metabolic alkalosis acidosis or they have no metabolic problem. Even if their CO2 was 180 and their pH 6.2, unless they've had time to compensate, their base excess should be 0, which tells you they don't have a metabolic problem. Their problems are all on the respiratory side. Don't hurt your brain by thinking what the metabolic problems are. Does that make sense? Does everyone get what that number means now? All right. So now when you see it on a blood gas, you know why it's there. Just as an aside for any true acid-base sticklers, if your CO2 was 180 and even without compensation, you'd probably have some degree of base excess. And I'm not going to go into the reasons why. I just don't want to receive letters saying you don't know what the frig you're talking about. So yes, I know. But for the purposes of the example I'm given, the point remains. Yes, sir. It's as reliable as anything else. And I'm going to tell you how that number actually fits into clinical use. It's as reliable or not reliable as anything else. It's certainly as reliable as the Henderson-Hasselbalch calculations you're doing, because what you'll see very shortly is they're identical. There's really no difference between them. They call it the base excess kit. It really is a further generation of that concept. There's the blood gas analyzers now understand whether it's a venous sample or an arterial sample and make up for the fact that there's some buffering of the hemoglobin on the venous side that's not there arterially. It makes up for the fact that even though we're pretending this is a plasma volume representation, it takes into effect that there's additional buffering in the interstitium. So it's more complex than I'm making out now, and each blood gas analyzer has their own equations for making this work, but the answer is it's pretty good. All right, this is a gamblegram, and this is what I showed you up front. And all it's representing is the neutrality, the fact that on one side you have your positive charged items, on the other you have your negative. And what you're really seeing here is that a huge portion of your positive charge is coming from sodium with some additional contribution from your Ca, your magnesium, your potassium. And they have the H plus there, and they have it in the same font as the others. But H plus is measured in nanograms, while everything else is usually measured in millimoles or milligrams. It's an order of magnitude difference. Even though we're looking at pH for everything, which is an inverse logarithmic rate representation of the amount of H plus, the amount of variance in H plus is on the nanoscale. Your body is so tightly regulated by buffer systems that the pH is going infinitesimally higher to make radical changes in pH, and opposite when you get alkalotic. So it really should be like an infinitesimal dot in that box is how much H plus is contributing to the actual positive charges of this diagram. Then on the negative side, a large part is chloride. And there's your bicarb. There's your weak acids, which I said primarily is albumin, and a little phosphate there too. And then the really small stuff like sulfate. Again, the hydroxyl group is infinitesimally small, just like the H plus. And this is kind of a crappy diagram. Now, why is this a crappy diagram? You'd be really smart if you could figure it out. That's a good answer. Good answer. The reason I found it crappy in particular is this is like predicated on 1940s lab technology, because there's a lot of stuff that we have the ability to measure easily that's not up here, right? For instance, lactate. Yeah. So this is a better representation for me because we're not in the 1950s anymore. It doesn't take 3 days to get a lactate back. I don't have to pretend lactate's part of that strong ion gap anymore. Lactate is right up there with chloride and something I should be measuring for every acid-base patient. So now, we don't even include that in the anion gap anymore, really, because I'm putting that right into my numbers right up front. But the concept still remains the same. You have to have positive charges and negative charges that are neutral. If chloride goes up, you're acidotic. If sodium is greater in representation of chloride, you're alkalotic. If you can't measure something and it's a strong ion, that's going to affect acid base. If your albumin concentration is varying, that's going to affect acid base. And we're not even talking about the CO2 side, because the respiratory part of this is going to be mentioned only in passing at the end. So then, now that we have all this, now that very little of this is making sense to you, but you have the terms percolating in your head, let's put this in real terms. All right, So I think that's more than enough for the first part of this. Again, go read that article I have linked in the show notes. You could print out the acid base sheet you're going to use in part 2 as well. Start getting an idea how that's going to look. And I will stop here and say I hope you have a great week. And I'll try to get part 2 up before the 2-week mark so we can kind of keep some continuity going. We'll see how that plays out. So Scott Weingart for the EMCrit podcast saying bye-bye.